Our first example of Shadama is a simple physics simulation of particles and gravity. As in the Logo programming language, we refer to mobile objects as turtles. Here we declare a breed of turtles such that each turtle will have properties X, Y, R, G, B, and A. A method is defined with the keyword def. Methods are executed on each turtle in a breed. Here we've defined the setColor method to use the turtle's X and Y coordinates to assign them a red and green value. In the static function setup, we set the number of turtles in the breed to be 3000 and then set all turtles' X and Y coordinates to be a random number between 0 and 512. We run setup by hitting Command S. Those dots may be hard to see, but we can increase the number of turtles to 30,000, 300,000, or 1 million. What we want to do next is move those turtles around, so we define a method called move. Move increments the X and Y of the turtles. We call the move method from a static function, step. When we click the step clock, step is repeatedly executed and the turtles move. Interestingly, while they're moving, we can edit the program on the fly and the changes take effect as soon as we hit Command S. We can add an argument to move, use it in the code, change the call site, and the turtles that went off screen come back. We can even allow each individual turtle to have its own velocity. So let's add properties dx and dy to each turtle. Then we use them in move. Here, instead of n, we increment the x and y of each turtle according to their dx and dy. We call the primitive fillRandom to set the dx and dy to be the x and y components of a randomly chosen direction vector. Now all turtles move in their own individual directions. Let's run it again by executing setup manually. Now we'll change this to be a simple gravity simulation. To do so, we'll add constant acceleration to the y component of the velocity. Now all turtles are accelerating towards the bottom. We don't want those particles to go out of bounds, so we modify the move method. First we store dx and dy as well as the possible new location of x and y into local variables. When new x is out of bounds, we make the turtles bounce back. When new y is out of bounds below, we wrap the value around to the top. After adjusting these variables, we write the values back to the turtle's properties. Now 1 million turtles are falling down, bouncing off the sidewalls and wrapping around to the top. We are now going to create a simulation with large objects. To do so, we use what's called a patch. A patch is the 2D grid of cells where turtles can store values. Here we create a patch called field and add R, G, B, and A properties for each cell. And we define a breed called filler that operates on the field. Now we define a method called fill. The argument for this method is the patch, and turtles executing this method update the patch cell value at their x and y coordinates. We modify setup to use a primitive called fillSpace, which creates turtles of the filler breed and places them at all integral grid points. When this setup is called and the fill method is called, each R and G of the patch get values derived from its position, resulting in this color gradient. Let's make some shapes now. We define the fillCircle method to replace fill. Let's also add the clear method, which clears the field's values. FillCircle works by having each filler turtle check whether it is within the radius of the circle. If it is, it writes the value into their corresponding cell. In the setup function, we call fillCircle and get a circle at 100, 100. Shadama programs can also be interactive. Let's split the setup function and create another one called loop. Notice to the right that there is a variable called mouseMove, which changes its value as we move the mouse pointer in the display. This is an indication that we can use the value in our program. Now let's tie it all together. This code has methods we used previously, such as setColor. FillCircle is slightly modified so that it sets normal vectors for the circle in the patch. In the move method, each turtle checks the normal in the patch cell where the turtle is located and computes a new direction from the dot product with the normal. When we run this, particles bounce off the circle and make a beautiful pattern. However, it is a bit hard to see because the colors of the turtles are too similar. Here we change the setColor method so that instead of using x and y position, we use the velocity dx and dy to determine the turtle's color. Then we call setColor from loop so that the colors are updated continuously. Here, horizontal velocity corresponds with reddish color and vertical velocity corresponds with greenish color. The visualization can be quickly adjusted to match how you prefer to view the simulation. For fun, you can make two circles that move symmetrically. Here's an interesting variation of our program. Instead of modeling gravity as pulling downward, gravity follows the inverse square law in relation to the mouse pointer location. It looks like there are large structures, but it's actually just 250,000 particles from regular initial positions, all following the inverse square law. Shadama allows the user to import images. The built-in fill image takes an image object, creates enough turtles to cover it, and sets the turtle colors based on the image's pixel values. This looks like an image, but it's actually a bunch of turtles. We reuse our previous move method, set the direction vectors randomly, create the loop method that calls move, and then run loop. For fun, we can use the turtle's red and green values to determine turtle velocity, causing an interesting effect. Let's use those pixels in our gravity simulation. The code checks the timer, and every 10 seconds it gathers all turtles to their original position. We can also try some mathematical functions. This is a program to visualize the Mandelbrot set. Notice how we can change the color scheme on the fly. And this is Conway's Game of Life. Again, we can change the program while the simulation is running, and the code changes are reflected in the simulation right away without needing to restart.